Hi guys! Tonight we're following a heavy, secretive element from the quiet places where it first slept in dark rock. Yellow dust, cold mountain veins, and stones that seem too beautiful to be ordinary. What if the thing that later reshaped war, medicine, electricity, politics, and fear began not as a machine, not as a bomb, not even as a theory, but as a curious mineral in someone's hand? You can almost see it now, a dull green-black chunk turned beneath candlelight, a strange yellow stain clinging to stone, a miner's lamp trembling in a tunnel where water taps slowly from the ceiling. Nobody hears atoms whispering. Nobody sees danger glowing. Not yet. So, before you settle into the story, take a moment to like the video and subscribe, and as you get comfortable, comment where you are listening from and your local time. It is always strange and lovely to imagine people drifting into history from kitchens, bedrooms, buses, and late-night corners of the world. Now, dim the lights, and let yourself step onto a cold hillside long before uranium has a name. You stand where the air's thin and damp, where the ground smells of wet moss, iron, and broken stone. Your boots press into mud darkened by old rain. Somewhere nearby, a stream works patiently over rocks, making that soft, glassy sound that has soothed human beings for thousands of years, because water is basically the planet's first sleep machine. Around you, hills rise with forests and exposed cliffs, their surfaces streaked with mineral colours, rusty red, chalky white, smoky grey, and sometimes, if you know where to look, odd patches of yellow and green that seem almost painted on by a very moody artist. Long before modern chemistry, people noticed these colours. Of course they do. Humans are wonderfully nosy creatures. Give someone a shiny pebble and 5 minutes later they're wearing it, trading it, grinding it into powder, or confidently telling a neighbour it cures sadness, toothache, and bad luck. Across many ancient societies, minerals are valued for colour before composition. Ochre gives red and yellow pigments, malachite gives green, lapis lazuli gives blue to the wealthy and the dramatic. Among the hidden minerals of the earth are uranium-bearing stones, including pitchblende, later called uraninite, and bright secondary minerals such as autumnite and torbanite, whose colours can look almost unnatural lemon yellow, apple green, sometimes glassy, sometimes dusty, sometimes as if moonlight got trapped in a crust of rock. You reach down and touch a rough stone. It is cool, grainy, and heavier than you expected. That heaviness matters, though nobody here can explain it yet. Uranium is a dense metal, and in some of its ores the weight feels quietly suspicious, as though the stone has swallowed more earth than its size allows. You turn it over in your palm, it leaves a faint mineral smell, metallic and dry, the scent of old tunnels and struck flint. There is no warning label, no Geiger counter clicking like nervous teeth, no scientist in a white coat rushing toward you with paperwork. There is only colour, weight, texture, and curiosity. In ancient and medieval mining regions, people dig for silver, copper, lead, tin, and iron. They follow veins through mountains with hand tools, oil lamps, wedges, ropes, and stubborn hope. In places that will later become famous for uranium, especially parts of Central Europe, miners are not searching for uranium at all. They are looking for metals they understand and can sell. The dark mineral pitchblende can appear in silver mines, frustrating workers because it often signals the end of rich silver ore. Imagine that. A stone that future empires will fear and hoard is, at first, basically the geological equivalent of a bad review. The miners see it and sigh. How rude of the earth. How rude. You walk into one of those early workings in your imagination. The tunnel ceiling is low. The air is close and sour with sweat, smoke, damp timber, and mineral dust. Every small sound is enlarged the scrape of a pick, the creak of a basket, a cough travelling through darkness, water dropping into a hidden pool. Your fingers brush the wall and come away gritty. The lamplight moves over black rock with a dull, greasy shine. That is part of the origin of the name pitch blende. It has the look of pitch, dark and tar-like, and it confused miners by blinding or deceiving them, because it did not yield the silver they wanted. This is the first mainstream historical fact to carry gently with you tonight. Uranium was not first treasured as a source of vast energy. It entered human attention through minerals and mines, especially as a byproduct or nuisance in ore deposits where people pursued other metals. The element itself remained unknown, hidden inside chemical forms. People handled its ores without knowing the atomic story locked within them. They saw stone, pigment, and mining trouble. They did not see nuclei. Yet the strange beauty of uranium minerals attracts attention in another way. Some uranium compounds have bright colours, and long before radioactivity is understood, minerals containing uranium are collected, admired, and sometimes used in pigments. Picture a cabinet of curiosities in a scholar's room: shells, fossils, dried plants, bones, coins, crystals, perhaps a mineral sample from a faraway mine. The room smells of wax, paper, dust, and old wood. A candle flame trembles. The collector lifts a yellow-green specimen and feels the pleasure of owning something rare, something that looks like a secret. There is no panic. There is just admiration, and possibly a very serious gentleman saying, "Remarkable," which was the old-fashioned way of screaming. This brings you to a quirky tidbit from the edge of early mineral culture. Some uranium minerals can fluoresce under ultraviolet light, glowing with vivid green or yellow tones. The people of the ancient world did not have ultraviolet lamps, obviously, unless someone has been hiding an extremely advanced Roman nightclub from us. But the property helps explain why later collectors became so fascinated by these minerals. Under certain light, they seem alive. Not alive like a creature, but alive like a dream pretending to be geology. Even today, collectors sometimes display fluorescent minerals in dark rooms, where stones that look sleepy in daylight suddenly shine like tiny enchanted landscapes. But there is a scholarly uncertainty here, soft and important. Historians still argue whether some very early mineral pigments and glass colorants contained uranium intentionally, or only by accident. The difficulty is that ancient craftspeople often used complex mineral mixtures without modern chemical names, and surviving objects may contain trace elements from the natural source material rather than deliberate choice. So when you imagine a potter grinding a yellow mineral or a glassmaker mixing ingredients near a hot furnace, you should not picture them saying, "Ah yes, uranium, atomic number 92. They are thinking in colour, heat, texture, and tradition. They know what works because someone taught them, and because hands remember what words do not." Now you move farther back, away from named mines and written records, into the longer human relationship with stone. You're beside a fire in deep evening. The smoke smells sharp and resinous. Sparks climb into black air. Someone nearby holds a coloured mineral against the flames. It catches a brief glint, yellow or green or black. People have always found meaning in unusual stones: a heavy pebble, a bright crystal, a rock that stains the fingers, a lump that melts into metal when heated in the right way. These things invite stories. Before the periodic table, the Earth is not a list of elements. It is a personality. It gives hides, tricks, stains, heals, poisons, and sometimes sparkles in a way that makes everybody slightly unreasonable. Uranium belongs to that older world before it belongs to science. It is born in stars, though nobody in the hillside knows this. The atoms under your feet were forged in violent cosmic processes billions of years ago, then folded into the young Earth, scattered through crust and rock, concentrated slowly by geological forces. That is almost too large to hold in a bedtime thought. So let it settle gently. The stone in your hand is older than language, older than agriculture, older than the first city wall, older than the first lullaby sung beside a cradle. It has been waiting through ice ages, forests, extinctions, migrations, kings, plagues, ships, and prayers. And yet, for most of human history, it remains anonymous. There is something peaceful about that. Uranium is present, but not central. It sits in the ground while farmers bend over fields. It lies in mountains while caravans cross deserts. It rests inside rock while temples rise. Books are copied, cities burn, and children chase dogs through alleys. Its power is real, but unrevealed. The world is full of such hidden forces. People live above them, sleep beside them, build houses from them birdway, and make myths around them. You keep walking through the damp mineral landscape. The sky lowers into evening. Pine needles release a clean scent underfoot. A raven calls once. Then the sound falls away into mist. You can imagine a miner ending his day with sore shoulders and blackened hands, not knowing that one disliked ore in the tunnel will someday become a word spoken in laboratories, parliaments, classrooms, deserts, hospitals, power stations, and nightmares. For him, the stone is stubborn. For a collector, it is curious. For a craftsperson, may be useful. For future humanity, it will become a mirror, showing intelligence, ambition, fear, hope, and the rather awkward habit humans have of discovering something powerful and immediately asking, can we make this bigger? But here, at the beginning, nothing explodes and nothing hums behind fences, nothing splits. The element waits without drama. It is mixed into mineral bodies, locked with oxygen, lead, radium traces, and other companions in the patient chemistry of the crust. The ground is cold beneath your feet. The air tastes faintly metallic. In the fading light, a patch of yellow mineral on a broken rock seems to hold the last of the sun. You look at it, and you understand why human beings noticed such stones long before they understood them. Beauty often arrives before explanation. Wonder gets there first, wearing muddy boots and carrying a candle. So you leave the hillside slowly, carrying only the image of a heavy dark stone and a soft mineral glow. No one has named uranium yet. No one has measured its hidden fire. The story is still quiet enough for sleep, still wrapped in earth, rain, moss, and the small sounds of mining tools in distant mountains. The element that will change humanity is not yet a headline, not yet a weapon, not yet a promise of electricity. It is simply part of the world beneath you, waiting in silence. While night settles over the rocks, you find yourself in a room warmed by coal, candle flame, and restless curiosity. Outside, the late 18th century moves with carriage wheels, church bells, muddy streets, and the careful footsteps of people who believe the world can finally be sorted into reason. Inside, the air smells of vinegar, smoke, old paper, hot metal, and the sharp mineral bite of acids. Glass vessels crowd the benches. Crucibles sit like small black cups beside balances, powders, notes, and stains that will absolutely never come out of that table, no matter how sternly someone wipes it. This is the age of Enlightenment chemistry, when learned people begin to stop treating matter as a mysterious soup of earth, air, fire, and water, and start asking what things are made of in a more exact way. You hear the faint clink of weights on a scale. You see a hand adjust a flame. You feel the chill of the floor through your shoes, because laboratories are rarely cozy in the way paintings pretend they are. They are smoky, drafty, dangerous places where clever people breathe questionable fumes and call it progress. In Berlin, in 1789, the chemist Martin Heinrich Klaproth studies a dark mineral known from mining districts. Klaproth is patient, precise, and unusually careful for an era when some experimenters behave as though eyebrows are optional. He analyzes the mineral, treats it with acids, heats it, separates residues, and observes results. From this work, he identifies what he believes is a new element. He names it uranium, after Uranus, the planet discovered only 8 years earlier by William Herschel in 1781. The naming is wonderfully fashionable. A new planet appears in the heavens, so a new earthly substance receives its name. Science, like everyone else, enjoys a trend. You stand beside Klaproth's workbench in imagination. The flame makes little breathing sounds. A spoon scrapes powder into a vessel. The room is tense but quiet, the kind of quiet made by concentration rather than peace. Black mineral becomes yellowish compounds, then darker residues, liquids cloud and clear. The chemist watches matter change and tries to understand what has remained constant underneath the transformations. It is not glamorous in the modern movie sense. Nobody shouts, "I have changed destiny." A more likely scene is a man leaning forward, frowning at a sample, then writing very carefully while the room smells unpleasantly of chemistry. Here is the mainstream historical fact resting at the centre of this moment. Klaproth did not isolate pure metallic uranium. He identified uranium in the form of an oxide, a compound containing uranium and oxygen. For decades, scientists believed they had the element itself, but what they truly possessed was not the pure metal. Only in 1841 did Eugène Melchior Péligot, a French chemist, isolate metallic uranium by reducing uranium tetrachloride with potassium. So the newborn element entered science slightly disguised, which feels appropriate for uranium. It arrived wearing a mask and let everyone congratulate themselves anyway. You can almost forgive them. Chemistry in the late 18th century is changing fast, but it is still learning its own grammar. Antoine Lavoisier has helped reshape chemical thinking, emphasizing measurement, conservation of mass, and clearer naming. Old ideas about phlogiston, that imaginary fire-like principle once thought to escape during burning, are being pushed aside. Oxygen is taking its place in explanation. Elements are becoming defined not by ancient philosophy, but by what can and cannot be decomposed by chemical means. It is a thrilling time, though thrilling here means slow, smoky, and full of glassware that might crack at the worst possible moment. You touch the edge of the bench, it is rough and cool where acid has scarred the wood. A draught enters under the door, carrying the scent of wet street and horse leather. Somewhere beyond the walls, Berlin continues with its ordinary life vendors calling. Wheels grinding over stone, someone hurrying home with bread wrapped in cloth. Inside the laboratory, the naming of uranium is a small intellectual ceremony. The universe has expanded outward with a newly recognized planet, and inward with a newly recognized substance. Sky and stone seem to answer one another. There is a quirky detail here that feels almost too charming for such a heavy element. Klaproth also discovered or helped identify several other elements, including zirconium and cerium, making him something like a collector of new names from stubborn minerals. In 1789, the same year associated with revolution in France, he presents uranium to the scientific world. While politics shakes Europe loudly, chemistry quietly adds a future giant to its list. History enjoys this sort of dramatic scheduling. Cannons in one direction, crucibles in another. Very balanced, if you ignore all the chaos. The name uranium carries a particular 18th century elegance. Uranus, the planet, had challenged the old visible boundaries of the solar system. For most of human history, people knew only the planets visible to the naked eye. Herschel's discovery stretched the map of the heavens. Klaproth's name choice turns that celestial surprise into a chemical tribute. You look at the little dish of yellow compound and imagine the cold blue-green planet far away, moving silently through darkness. The connection is poetic, even if the substance on the bench is not especially poetic to handle. It is more powder, stain, and cautious note-taking than starlight. Still, the misunderstanding remains. Scientists know uranium is heavy, They study its compounds. They observe colours, reactions, and salts. But they do not know about radioactivity. They do not know about atomic nuclei. They do not know that this element is unstable in a deep, slow, natural way. Their instruments cannot hear the quiet emissions moving through matter. To them, uranium is chemically interesting, dense, unusual, and useful mostly as another entry in the expanding catalogue of nature. The atom is still imagined as far more solid and indivisible than it really is. A locked room has been found, but no one has noticed the trapdoor. Historians still argue whether Klaproth's reputation for precision has been slightly softened by the later realization that his uranium was an oxide. Some scholars emphasize that his identification was a brilliant achievement within the methods available to him. Others gently point out that the word discovery can become slippery when the discoverer does not isolate the pure element. This is not scandalous. It is just science being science, which often means walking confidently into a fog and then naming the fog. You move now through shelves of mineral samples and handwritten papers. The atmosphere is dry, dusty, and alert. A clock ticks with great seriousness, as if it too is participating in research. The labels are written in careful ink. Some are in Latinized forms, some in German or French, some using names that will change as chemistry becomes more standardized. Scientific language is not yet the neat international system students memorize later. It is a crowded marketplace of terms, traditions, rival theories, and personal pride. Naming a substance is not just a technical act. It is a claim, a small flag planted in nature. And what a strange flag uranium becomes. At first, it seems to fit comfortably among other mineral discoveries. It joins the expanding family of known elements. It becomes part of lectures, samples, and chemical experiments. There is no immediate transformation of society. No mayor cuts a ribbon beside a glowing reactor. No one builds policy around it. It is a curiosity with weight and colour, respectable but not yet terrifying. If the element could nap, this would be one of its drowsier public moments. Yet you can sense a quiet shift in how humans are approaching the material world. Instead of simply using stones for pigment, ornament, or metal, scholars now attempt to separate, classify, and define. The mineral is no longer only something found in the ground. It becomes evidence. It becomes a question. It becomes a name in a table, and a name in a table is more powerful than it looks. Once something is named, it can be compared, ordered, bought, taught, misused, celebrated, and investigated by people who will never see the original rock. You lean closer to the flame. Heat brushes your face. The glass glows amber at the edges. The tiny sounds of the laboratory continue, paper shifting, liquid dripping, tongs tapping ceramic. The world outside is full of kingdoms, arguments, trade, poverty, salons, farms, wars, and music. But here, under wavering light, matter itself is being persuaded to reveal pieces of its identity, slowly, reluctantly, with stains. Klaproth's uranium is not yet the uranium of the modern imagination. It is not yet a symbol of apocalypse or energy. It is a new chemical substance named for a new planet, a child of both mining and astronomy. Discovered in an era that believes knowledge can tame confusion. The belief is beautiful and a little overconfident, which is a very human combination. You watch the chemist write the name, and the ink darkens on the page. Uranium. A word settles into history. Soft at first, almost harmless, like a seed falling into soil. The lamps burn lower. Coal heat fades into a dull red. The room smells of cooling ash and mineral dust. You step away from the bench while the new element rests in bottles, notes, and uncertain understanding. It has been recognized, but not understood. It has been named, but not revealed. In that gap between naming and knowing, humanity often feels safest. The bottle is corked, the label is neat, the scholar is pleased. Outside, night gathers over Berlin, and somewhere beyond the clouds, Uranus continues its slow pale orbit, unaware that a dense earthly element now carries its name through the sleeping city. You step into a 19th century workshop where the windows are tall, the floorboards are worn smooth, and the morning light arrives through a veil of coal smoke. The room is not dramatic at first glance. It is filled with shelves, pots, moulds, barrels of sand, sacks of mineral powders, and glass rods resting like frozen honey. Yet there is a quiet enchantment here. You hear the furnace breathing in the corner, a low, steady roar like some polite dragon trying not to interrupt. Heat presses against your cheeks. The air smells of ash, metal, damp clay, and a faint chemical bitterness that seems to cling to the back of the throat. On a work table nearby, a craftsman lifts a small scoop of yellow powder. It is not treated as a miracle. It is not handled as a world-changing danger. It is simply material, bought, measured, mixed, and folded into craft. In the 19th century, uranium compounds are used to colour glass and ceramics, giving them shades of yellow, green, orange, and sometimes a strange oily amber that catches the light in a way that feels almost too lively. The element has stepped out of the mineral cabinet and into parlours, dining rooms, apothecary shelves, and decorative art. It has become beautiful, useful, marketable, and, very inconveniently, misunderstood. You watch as the powder is added to a batch of molten glass. The furnace glows white-orange, and the heat has a physical weight, pressing through your clothes, drying your lips, warming the little hairs on your arm. Tools scrape and ring. A rod turns slowly. The molten glass gathers at its end, bright and syrupy, as if sunlight has been melted into a droplet. With breath and motion, the glass swells into a vessel. The craftsman shapes it, rolls it, clips it, reheats it, and turns it again. Every movement is practiced, patient, almost sleepy in rhythm, though one careless gesture would make the day much less charming. This is one of the most ordinary and fascinating transformations in uranium's public life. It does not enter the 19th century home as a symbol of physics. It enters as colour, a cup, a bead, a plate, a vase, a decorative bowl sitting on a lace-covered table while someone serves, preserves, and pretends not to judge the neighbours. Uranium glass becomes prized for its yellow-green appearance, and later generations will often call certain forms Vaseline glass because of the resemblance to petroleum jelly. Under ultraviolet light, many uranium glass objects fluoresce a vivid green. The glow can be startling, like the object has remembered a secret in the dark. Of course, most 19th century owners are not shining ultraviolet lamps on their tableware. They admire the glass by candlelight, daylight, and gaslight. Imagine a drawing room in the evening. The carpet is thick, the curtains hold the smell of smoke. A clock ticks on the mantel. Cups and small dishes glimmer on a sideboard, their pale green surfaces catching the flame of a lamp. Fingers touch the rim of a glass, smooth and cool, faintly heavier than expected. No one sees invisible emissions leaving the material. No one pauses during dessert to say, perhaps this fruit bowl is making a quiet scientific argument. That would ruin the mood, honestly. The mainstream fact here is simple, but important uranium compounds were widely used in decorative glass and ceramic glazes during the 19th century, especially to create bright yellows and greens. Factories in Europe and elsewhere experimented with uranium oxides as colorants, and potteries used uranium-based glazes to achieve rich oranges, reds, and yellows. These objects were not rare laboratory oddities. They were part of a growing consumer world, a world where industrial production met middle-class taste, and novelty could be placed directly on a dining table. You move from the glass house to a pottery workshop where the atmosphere changes. Here the heat is drier, the dust softer, the smell earthier. Clay waits under damp cloth. brushes sit in jars. Fired pieces line shelves in rows, pale and patient, like they are listening. A worker mixes glaze in a shallow basin, stirring until the liquid has the thickness of cream. Mineral pigments enter the mixture. Uranium compounds can make colours that feel warm and lively, especially in glazes that emerge from the kiln with orange or yellow brilliance. When a decorated plate is lifted after firing, its surface shines under the light, hard and smooth as still water. You reach toward it, and the plate is warm, not burning, just holding the memory of fire. There is something intimate about ceramics. Glass feels like captured light, but pottery feels like earth persuaded into usefulness. A uranium-glazed object sits at the crossing point of geology, chemistry, commerce, and domestic life. It may hold soup, it may decorate a shelf, it may be praised for fashionable colour by someone who does not know that the colour has a deeper story. The object is both charming and unsettling, though only one of those qualities is visible at first. A quirky tidbit slips quietly into this glowing world. Some collectors today use small ultraviolet flashlights to hunt for uranium glass in antique shops. A shelf of ordinary-looking old glass can suddenly flare green under the beam, and the scene becomes part treasure hunt, part science lesson, part very mild ghost story. It is oddly satisfying. There you are, standing between dusty teacups and chipped sugar bowls, and suddenly one little dish shines like a radioactive lime. The levels of radioactivity in many uranium glass pieces are generally low, but the emotional effect is enormous, because nothing says calm Sunday browsing like discovering your grandmother's candy dish has a secret nightlife. The 19th century loves this kind of hidden marvel. It is an age of exhibitions, catalogues, public lectures, improved instruments, and industrial display. People gather to see machines, chemicals, electric demonstrations, exotic materials, and manufactured wonders. New colours matter. Before modern synthetic dyes become common, brilliant stable colours can be difficult and expensive. Chemistry gives artists and manufacturers fresh tools. Uranium is one of many substances that enter the expanding palette of industry, along with chromium greens, cobalt blues, cadmium yellows, arsenic greens, and other pigments that make history look vivid and also slightly alarming. You continue into a photographer's workspace. The mood becomes quieter. The furnace is gone, replaced by trays, bottles, paper, glass plates, and a dim reddish light. The room smells of wet paper, alcohol, dust, and chemical solutions. You hear the soft slide of a tray, the drip of liquid from tongs, the tiny slap of paper against a drying line. Photography in the 19th century is still young, experimental, and full of processes that require patience and excellent tolerance for mysterious stains. Uranium compounds appear in some photographic practices, including toning and intensifying images. They are part of a broader culture in which photographers try different metals and salts to alter contrast, colour, permanence, and effect. You lean over a tray as an image slowly deepens. A face appears out of pale fog, a street, a hand, a tree, a vanished afternoon. There is something almost supernatural about early photography, even without radioactive materials wandering into the recipe. To watch an image form in chemicals is to watch memory become physical. Uranium's role here is not as famous as silver, which sits at the heart of many photographic processes, but it belongs to the experimental atmosphere of the period. The element is still more craft ingredient than cosmic force, still moving quietly through trades that care about colour, image, and surface. Historians still debate how much ordinary consumers understood about the materials in these objects. Did buyers know the bright glass or glowing glaze contained uranium, or did they simply trust colour names, merchant claims, and fashionable appearance? In many cases, the chemical content mattered more to manufacturers than to owners. Labels were inconsistent. Recipes could be guarded as trade knowledge. Objects circulated through shops and homes detached from the mineral stories that produced them. The uncertainty is not only about paperwork, it is about everyday awareness, the soft gap between what industry uses and what households imagine they possess. You pass through a shop filled with finished wares. The bell over the door gives a small bright ring. Outside, horses move over wet stone streets. Inside, the shelves sparkle. A woman lifts a pale green glass vase and turns it in the window light. A clerk praises the colour. A child presses a finger to a glazed tile, then is gently told not to touch. Because childhood has always been a long negotiation with fragile objects, the atmosphere is ordinary, but history hides in ordinary rooms very well. It does not always arrive with thunder. Sometimes it arrives as a fashionable vase wrapped in paper. The deeper irony is that uranium's decorative life depends on ignorance, but not foolishness. People are not stupid for missing what cannot yet be measured by common tools. They are living inside the limits of their age. Their senses tell them the object is beautiful, solid, smooth, and useful. Their culture tells them chemistry is improving life. Their markets tell them novelty is desirable. The invisible part remains invisible. That is one of the gentler warnings history offers. In its calm but slightly smug voice, every age has invisible parts. By evening, the workshop cools. The furnace dims from white to orange to a sleepy red. Glass objects rest in the annealing chamber, slowly releasing stress so they will not crack. Pottery waits on shelves. Photographic prints hang like quiet ghosts in the dark room. Your hands remember the textures: slick glaze, dusty powder, warm glass, damp paper. Your nose holds the layered scents of coal smoke, clay, vinegar, and chemical baths. Around you, uranium has become domestic and artistic, entering the world not with fear, but with colour. You leave the shop as gaslights bloom along the street. Their halos tremble in the mist. Behind the windows, greenish glass catches the glow and gives it back softly. The element sits in cups, tiles, lenses, powders, and plates, admired for surfaces while its deeper nature remains hidden. It is still a servant of beauty, still a pigment, still an industrial curiosity, and in that half-lit 19th century room, where objects shine gently and nobody hears the atom's quiet unrest, uranium becomes part of daily life by pretending to be only decoration. You enter a room where the light is low, the curtains are drawn, and the air carries the dry smell of dust, paper, varnished wood, and chemical salts. It is the late 19th century, and science has grown confident enough to be charmingly surprised by itself. Tables hold glass plates, metal foils, minerals, notebooks, and little instruments with needles that tremble at the edge of understanding. Outside, wheels pass over wet streets. Inside, the room is quiet except for the scratch of a pen, the soft click of a drawer, and the occasional sigh of someone realizing nature has once again refused to behave politely. You stand near a desk in Paris in 1896 where Henri Becquerel is studying uranium salts. The recent discovery of X-rays by Wilhelm Röntgen has stirred scientific Europe into excitement. Invisible rays that pass through flesh and reveal bones. Very tasteful nightmare material. Researchers everywhere begin testing glowing substances, phosphorescent materials, minerals, screens, and plates, trying to understand whether strange light and invisible energy are connected. The mood is electric, though the lamps are still ordinary, and the people in the room are still wearing far too many layers of clothing for laboratory work. Becquerel wraps photographic plates in black paper. He places uranium salts on top, expecting sunlight to help produce some effect, perhaps because the salts are phosphorescent. Then the weather refuses to cooperate. The sky turns cloudy, and the sun hides behind grey Parisian softness. So the wrapped plates and uranium salts are put away in a drawer. You can almost hear the drawer slide shut. Wood rubbing against wood, a small ordinary sound that history will later treat as if it were a drum roll. When Becquerel develops the plates, he finds strong images on them, even though they have not been exposed to sunlight. The uranium salts have emitted something invisible, something powerful enough to pass through the wrapping and fog of the photographic plate. This is the mainstream historical fact at the heart of the moment in 1896. Becquerel discovered that uranium compounds emit penetrating radiation without needing external light. The phenomenon will become known as radioactivity, though the name itself will be shaped in the work of Marie and Pierre Curie. The discovery is quiet, almost accidental, and beautifully inconvenient. Nature has opened a door in a drawer. You lean closer to the plate. The surface is smooth and cool, with that faint chemical smell of a dark room, a mixture of damp paper, developer, and metallic sharpness. An image has appeared where none should have appeared. It is not a ghost, though one understands why the century loved ghosts. It is evidence. Something has travelled invisibly from uranium into the plate. No flame, no sunlight, no spark, just a steady release from matter itself, as if the mineral contains its own inner weather. The discovery unsettles assumptions. Phosphorescence is familiar enough, some substances absorb light and later glow. But uranium does not seem to be waiting for sunlight. It emits these rays on its own. The atom, still imagined by many as indivisible or at least comfortably stable, begins to look less like a tiny hard bead and more like a locked house with noises in the walls. Scientists do not yet know about protons and neutrons in the modern sense. They do not yet understand radioactive decay. But the first clue has appeared, darkening a plate in silence. You walk through the world of late 19th century experimental physics, and it is tactile, fussy, and full of patience. Instruments are delicate. Measurements are often slow. A room must be arranged carefully. A draft can disturb an experiment. Dust can ruin an observation. Fingers must avoid touching treated surfaces. You feel the smooth edge of a glass plate between your hands. You hear the faint fizz of a chemical bath. You smell oil lamps, polished brass, old cloth, and acids carefully stoppered in bottles. Science here is not a glowing screen. It is a body leaning over a table, waiting for a mark to appear. Marie Curie enters this story with a different kind of attention. She studies Becquerel's rays and begins measuring the activity of uranium compounds with extraordinary care. Pierre Curie and his brother Jacques had developed an electrometer that could measure tiny electrical charges, and this instrument becomes essential. Instead of relying only on photographic plates, Marie Curie measures how uranium rays ionize air, allowing it to conduct electricity. That sounds neat and tidy, but imagine the work: physically samples prepared, air heavy in the laboratory, metal parts adjusted, notes written, readings checked again and again. Discovery arrives dressed as repetition. Her measurements show that radiation seems linked to the amount of uranium present, not to the chemical form of the uranium compound. That insight is enormous. It suggests the radiation comes from the atom itself, not from ordinary chemical reactions between substances. A chemical compound can change color, dissolve, crystallize, or react. Yet this emission remains tied to the element's inner identity. The word radioactivity will describe this property, and it begins to transform the scientific view of matter. The atom is not merely small, it is active. It has history. It can change into something else. You pass into the Curie's workspace, and any romantic image of a shining laboratory politely collapses. The room is poorly equipped, chilly in winter, hot in summer, and physically demanding. The atmosphere smells of coal smoke, damp walls, iron equipment, and chemical residues. There are heavy vessels, stirring rods, heaps of processed mineral material, and long hours that do not care whether anyone is tired. The Curies study pitch blende and notice that it is more radioactive than pure uranium would suggest. Something else must be inside it, something even more active. From this path come polonium and radium, elements discovered through exhausting chemical separation. A quirky tidbit glows faintly here. Early researchers sometimes treated radioactive materials with startling casualness. Radium samples could be carried in pockets, handled in small tubes, or admired for their glow. Pierre Curie reportedly liked demonstrating radium's effects, and early observers described radium salts giving off light in the dark. The glow became famous, almost magical. People saw beauty and promise, because people are very good at meeting danger and saying, "What a lovely colour." The later health risks were not yet fully understood, and enthusiasm moved faster than caution, which is basically humanity's unofficial motto. Yet not everything is simple in the historical record. Scholars still disagree over how accidental Becquerel's discovery truly was. The Cloudy Day Draw story is memorable and largely grounded in his own reports, but some historians argue that his prepared mind mattered more than luck. He knew what to test, how to recognize significance, and how to compare results. Chance may have opened the drawer, so to speak, but training allowed him to understand what was sitting inside it. Discovery often looks accidental only because the final moment is easier to narrate than years of preparation. The invisible rays soon become a subject of lively classification. Are they like X-rays? Are they particles? Are there different types? Ernest Rutherford, working at the turn of the century, helps distinguish alpha and beta radiation, and later gamma radiation is identified as another form. The names are modest, just Greek letters, as if labelling a dragon A, B, and C makes it less dramatic. Alpha rays are stopped more easily. Beta rays penetrate farther. Gamma rays are deeply penetrating electromagnetic radiation. The categories begin to give shape to the unseen. The silence from uranium is no longer a single mystery, but a family of behaviours. You imagine standing near an electroscope, watching thin metal leaves move apart when charged, then slowly collapse as ionized air allows the charge to leak away. The motion is tiny, but the meaning is vast. A needle shifts, a leaf trembles, a plate fogs. These are the soft gestures by which the atom confesses. The soundscape remains gentle pencil on paper, shoes on floorboards, rain ticking against glass. No grand machinery is needed yet. The universe is changing its explanation in a room quiet enough to hear someone breathe. The public, naturally, becomes fascinated. Invisible rays fit perfectly into an era already enchanted by electricity, spiritualism, photography, telegraphs, and strange forces that seem to pass through space. If an image can be sent, if a voice can travel by wire, if bones can be seen through skin, why not imagine matter glowing with secret power? Popular culture begins to blur science, miracle, and spectacle. Some people treat radioactivity as a symbol of modern wonder. Others see mystery. A few see profit. Because if there is one force more penetrating than gamma radiation, it may be marketing. For scientists, however, the implications are deeper and more unsettling. Radioactivity appears to be spontaneous. It does not require ordinary chemical fuel. It does not burn like coal or wood. It does not depend on heat from a furnace. It comes from inside the atom, steadily, according to laws not yet fully understood. This challenges older ideas of elemental permanence. If radioactive substances transform over time, then elements are not always fixed forever. Matter has a hidden clock. Uranium is not only a substance, it is a process, a slow unfolding. You stand in the dim laboratory as evening gathers. The glassware turns dark at the edges. The smell of chemicals fades into damp wood and cooling metal. Somewhere, a photographic plate lies wrapped and waiting. Somewhere, a needle hesitates above a scale. Somewhere, a mineral sample gives off emissions too quiet for the senses, but strong enough to alter instruments and ideas. The world outside still walks past in ignorance, buying bread, lighting lamps, closing shutters. Inside, the invisible has become measurable. A strange calm settles over the scene. Nothing here feels like destiny yet. It feels like careful work, puzzlement, patience, and a little scholarly stubbornness. You sense the tenderness of early discovery, the human hand placing a sample, the human eye noticing a mark, the human mind refusing to dismiss it. Uranium has begun to speak, not in light seen by the eye, but in traces, shadows, and disturbed air. Its voice is faint, but once heard, it cannot be unheard. The atom is no longer asleep in human imagination. It is restless, and the room is listening. You enter a laboratory where the air feels colder than the lamps suggest. The room is tidy in that peculiar scientific way, with neat benches, careful labels, and at least 3 objects that look as if touching them would be an immediate mistake. Brass instruments gleam softly. Wires loop over tabletops. Glass tubes rest in clamps. A faint smell of ozone, dust, warm insulation, and polished metal hangs in the air. Somewhere, a pump ticks with patient little breaths. Somewhere else, a needle trembles on a dial, as if matter itself has become nervous. The early 20th century is learning that the atom is not a tiny solid ball, despite the comfortable simplicity of that idea. Comfortable ideas do not survive long in physics. They are patted gently on the shoulder, thanked for their service, and then replaced by something stranger. You stand beside the scientists who are beginning to suspect that matter has internal architecture electrons, a nucleus, charge, mass, empty space, hidden order. The atom is becoming less like a pebble and more like a cathedral built mostly of silence. In 1911, Ernest Rutherford proposes the nuclear model of the atom after analysing results from the famous gold foil experiment conducted by Hans Geiger and Ernest Marsden. Alpha particles are fired at extremely thin gold foil. Most pass through, but a few bounce back at sharp angles. Rutherford later compares the surprise to firing a shell at tissue paper and having it return. You can imagine the scene without drama. At first a dim room, a zinc sulfide screen, tiny flashes counted by tired eyes, the dry smell of equipment, the ache of concentration. Yet those little flashes reveal something enormous. Most of the atom is empty space, and almost all its mass is concentrated in a tiny central nucleus. You pause with that thought. The table beneath your fingers feels solid. The floor seems steady. Your hand looks continuous, warm, complete. But every object around you is made mostly of emptiness, held together by forces your senses cannot feel directly. It is a wonderful bedtime thought, provided you do not think about it too hard while holding a teacup. The world is solid because invisible arrangements agree to act that way. Very polite of them, really. Uranium now becomes interesting not only as a radioactive substance, but as a clue to the inner life of atoms. Its emissions are not random magic. They are signs that nuclei can change. Alpha particles are helium nuclei. Beta emissions involve changes deeper still. Radioactive decay shows that one element can transform into another. This idea would have sounded almost like alchemy to earlier centuries, except now it arrives with measurements, equations, and laboratory notebooks, which makes it respectable and much harder to dismiss. You move through a corridor of discovery where each door opens onto another adjustment in human certainty. In 1913, Niels Bohr offers a model of the atom with electrons occupying specific energy levels. His picture is not the final word, but it gives physicists a way to connect atomic structure with spectra, those coloured fingerprints of elements. The laboratory glows with narrow bands of light through spectroscopes. You smell heated glass and dust on electric equipment. You hear the soft hum of current and the scratch of chalk on a board. Matter is becoming mathematical, which is impressive. though not especially considerate to sleepy students. The mainstream fact anchoring this stage is that nuclear physics developed through a chain of discoveries, not one single revelation. Rutherford's nucleus, Bohr's atomic model, the identification of isotopes, and later the discovery of the neutron all changed the way scientists understood uranium. The neutron discovered by James Chadwick in 1932 becomes especially important because it carries no electric charge. Since it is neutral, it can approach atomic nuclei without being repelled by positive charge. In plain language, it is the quiet guest at the atomic party who can get through the door without causing immediate social conflict. You stand near Chadwick's apparatus in imagination. Beryllium is struck with alpha particles, and an unusual radiation emerges. It knocks protons from paraffin wax, and careful measurements reveal that this radiation is made of neutral particles with mass close to that of protons. The discovery is elegant, but the room itself is physical and workmanlike cables, shielding, counters, handwritten data, the smell of wax, metal, and stale air. Scientific revolutions often smell less like lightning and more like old equipment. The neutron gives researchers a new tool. If nuclei can be struck by neutrons, perhaps they can be transformed. Enrico Fermi in Rome begins bombarding elements with neutrons in the 1930s. His group finds that slowing neutrons down, using substances such as paraffin or water, can make them more effective in triggering nuclear reactions. This is a beautifully odd fact in some cases. A slower neutron is more useful than a fast one. It is one of those moments where nature quietly says, "No need to rush," which is frankly good advice for everyone. A quirky tidbit lives inside Fermi's work. His Rome group was nicknamed the Via Panisperna Boys, after the street where their institute stood, though the boys were serious physicists doing work that would reshape the century. They experimented with improvised materials, including paraffin, and in one famous account, Fermi realized that placing a hydrogen-rich substance near the source changed the reaction rate dramatically. The path to nuclear power did not begin with sleek futuristic machines. It included waxy moderators, cramped rooms, and people trying things because the universe was being stubborn again. You followed the experiments toward uranium. Scientists bombard uranium with neutrons and think they may be creating new elements heavier than uranium, called transuranic elements. The idea is plausible. Uranium is the heaviest naturally occurring element then known in significant quantity. Add something to its nucleus. Perhaps you climb higher. The language of the time is filled with possible new elements, decay chains, activities, and uncertain chemical separations. You can feel the intellectual fog thickening. The lab smells of acids, damp coats, and hot electrical parts. Samples must be separated, measured, compared. The work is slow, and the answers do not line up neatly. Researchers still debate how much the scientists of the 1930s were guided by expectation when they interpreted uranium experiments. Some saw evidence for heavier elements because that was what theory encouraged them to look for. Others noticed chemical results that did not fit the expected pattern. The uncertainty matters because discovery is not simply seeing. It is also knowing what your mind is ready to accept. Nature can place the evidence on the table, and human beings may still squint at it and say, "Surely that cannot be barium." And then barium appears. In Berlin in 1938, Otto Hahn and Fritz Strassmann performed chemical experiments on uranium after neutron bombardment. They find evidence of barium, an element much lighter than uranium. Chemically, the result is astonishing. It suggests that the uranium nucleus has not merely been nudged into a heavier form, it has split into large fragments. Hahn and Strassmann are careful chemists, and their finding is so strange that it demands explanation beyond ordinary assumptions. Lise Meitner, who had fled Nazi Germany because of her Jewish ancestry, receives news of the results. With her nephew, Otto Frisch, she interprets the process physically. They realize that the uranium nucleus can split, releasing energy. Frisch names the process fission, borrowing from biology, where cells divide. You can picture Meitner and Frisch walking in winter, discussing the problem in cold air, snow underfoot, the world quiet around them while their thoughts move through the nucleus. The scene has become almost legendary. Two people, a difficult result, and a realization that a heavy atom can divide. The energy release makes sense through Einstein's relation between mass and energy. A small amount of mass is converted into a large amount of energy. The numbers are startling, not loud yet, not political in the room where they are first understood, but startling enough to change every serious conversation among physicists. The nucleus is not a sealed vault. It can be opened. Uranium is not merely emitting particles through slow decay. Under the right conditions, its nucleus can split abruptly, releasing neutrons that may strike other nuclei. You hear the phrase chain reaction begin to form in the scientific imagination. One fission event releases neutrons. Those neutrons may cause more fissions. More fissions release more neutrons. The idea is simple enough to explain, yet immense in consequence. It is like watching one candle light several others, except the candles are atoms and the room is made of mathematics, fear, and possibility. Even in a calm laboratory, the concept carries a chill. Not all uranium atoms behave the same way. Isotopes become crucial. Uranium-235, a rare isotope, is much more readily fissioned by slow neutrons than uranium-238, which is far more abundant. Isotopes are atoms of the same element with different numbers of neutrons. Chemically, they are almost twins, but their nuclei can behave very differently. You imagine two nearly identical keys, one that merely scratches at the lock, and one that opens a door no one is fully prepared to enter. The instruments grow more sensitive, counters click in irregular patterns, ionization chambers detect radiation, cloud chambers reveal tracks like ghostly scratches through vapor. In one room, charged particles pass through supersaturated mist and leave delicate trails, curling and branching like tiny weather maps. The air is cool and damp, your skin feels the chill, the glass walls of the chamber bead with condensation. It is beautiful in the way scientific evidence can be beautiful brief, precise, and slightly eerie. By the end of the 1930s, uranium has been transformed in human understanding. It is no longer only a heavy radioactive element. It is a nucleus capable of division. The atom is no longer indivisible in practice or imagination. The smallest architecture of matter has become a place where energy is stored, released, counted, and feared. Physics has moved from observing invisible rays to opening the structure that produces them. The laboratory settles into evening. Papers lie under lamps. Chalk dust softens the edges of the equations on a board. A coat hangs from a chair. Outside, street sounds fade into winter darkness. Inside, the atom has lost its old innocence. You stand in the hush and feel the strange tenderness of the moment human minds have reached into matter and found not stillness, but tension. Uranium has split in thought, in experiment, in language. The room is quiet, but the quiet is different now. It has become the silence just after a secret is understood. You step into wartime America, and the air changes at once. It feels louder, even in quiet rooms. There is the distant rumble of trains, the bark of factory whistles, the scratch of typewriters, the hard tap of military shoes across polished floors. Newspapers smell of ink and urgency. Offices smell of wool coats, cigarettes, floor wax, and coffee left too long on a hot plate. Everyone seems to be carrying envelopes, files, or secrets. Sometimes all three. The world has become tense enough that even science feels watched. In 1939, word of uranium fission reaches physicists who understand what it might mean. A bomb of extraordinary power may be possible if enough of the right uranium isotope can be gathered, arranged, and made to sustain a rapid chain reaction. The thought is almost absurd at first. The engineering challenge is enormous. Uranium-235 is rare, mixed with the far more common uranium-238, and chemically they behave so much alike that separating them is like trying to sort identical grains of sand by personality. Very convenient. Thank you, nature. Yet fear sharpens imagination. Some scientists worry that Nazi Germany may be pursuing atomic weapons. Refugee physicists, many of whom fled fascism in Europe, carry both knowledge and dread. The letter associated with Albert Einstein and Leo Szilard warns President Franklin D. Roosevelt that uranium might become the basis of powerful bombs. That warning helps push the United States toward organized research. The mainstream historical fact here is clear: the Manhattan Project became the secret wartime program that developed the first atomic weapons, bringing together physics, chemistry, engineering, military command, and vast industrial labour under extraordinary secrecy. You enter a government office where the blinds are half closed. Sunlight lies in pale strips across a desk covered with maps. A fan turns slowly, moving warm air and cigarette smoke around rather than solving anything. Men speak carefully. Names are shortened. Locations become codes. Budgets become hidden inside other budgets. Uranium is no longer simply a laboratory material. It is now a military problem, a production problem, a logistical problem, and quietly underneath all of that, a moral problem that no filing cabinet can hold. The project spreads across the landscape like a secret city being dreamed by engineers. In Tennessee, Oak Ridge rises behind fences and checkpoints. In Washington state, Hanford takes shape along the Columbia River for plutonium production. In New Mexico, Los Alamos gathers scientists on a mesa under a wide, bright sky. You feel dust on your shoes, pine resin in the air, the dry touch of wind against your face. A truck grinds along a road. Guards check badges. Floodlights hum at night. The places are real, but their purpose is hidden, even from many who work there. At Oak Ridge, uranium separation becomes a vast industrial effort. One method uses electromagnetic separation in machines called calutrons. Another uses gaseous diffusion, forcing uranium hexafluoride through barriers so that the slightly lighter molecules containing uranium-235 move just a little differently from those containing uranium-238. A third method uses thermal diffusion. Each approach is difficult, expensive, and hungry for electricity. The buildings are immense. Pipes run like metal vines. Gauges tremble. Motors drone. The atmosphere smells of machine oil, hot dust, damp concrete, and the metallic tang of newly built industry. You walk through one of these plants and feel how strange secrecy can be when it becomes physical. The floor vibrates through your shoes. The air is warm and dry. Women sit at control panels, watching dials and adjusting knobs. Many workers do not know exactly what they are producing. They are trained to keep readings within proper ranges, to report problems, to follow procedure, not to ask broad questions. In this way, the project divides knowledge into pieces. One person knows a valve, another knows a schedule, another knows a calculation. The full picture is guarded like a sleeping animal. A quirky wartime tidbit belongs here, and it sounds almost invented, but it is not. The Manhattan Project borrowed enormous quantities of silver from the United States Treasury to make electrical conductors for the calutron magnets, because copper was scarce and needed for the war. Silver bars, usually associated with volts and currency, were turned into coils and bus bars for uranium separation. Imagine wealth itself being reshaped into machinery, as if the nation emptied part of a treasure chest and said, "Please become magnet parts." History does enjoy being weird when nobody's looking. The workers at Oak Ridge live in a city that appears quickly, with prefabricated houses, muddy roads, cafeterias, dormitories, laundries, buses, and rumours. You hear swing music from a radio behind a thin wall. You smell fried food, wet wool, tobacco, soap, and red clay after rain. Shoes sink into mud because the new city grows faster than its sidewalks. People date, argue, laugh, get bored, miss home, and complain about the food. They also help build a weapon whose nature many of them do not know. Ordinary life sits directly beside extraordinary consequence, sharing the same cafeteria tray. You move west to Los Alamos, and the mood becomes sharper, higher, more exposed. The mesa air is thin and dry. Pinon smoke drifts from stoves. Dust gathers on windowsills. At night, the stars look close enough to make even brilliant people feel briefly small, which is healthy for them. Scientists work through calculations, designs, tests, and arguments. Chalk squeaks across boards. Papers pile up. Coffee cools in chipped mugs. People are exhausted and intensely alive. A problem solved at midnight may change the work of a factory 1,000 miles away. Uranium weapon design focuses on assembling enough uranium-235 quickly enough to create a supercritical mass, allowing a runaway chain reaction. The gun-type design is considered technically simpler than the implosion design required for plutonium. In the gun-type concept, one piece of uranium is fired into another, forming a configuration capable of explosive fission. The simplicity is relative, of course. Simpler in this setting still means requiring a hidden industrial empire, rare isotopes, advanced calculations, and enough secrecy to make everyone at dinner slightly suspicious. Scholars continue to debate how inevitable the Manhattan Project really was once fission was understood and war had begun. Some argue that fear of a German atomic weapon made the effort almost unavoidable in the minds of Allied leaders. Others emphasize that Germany's program was far less advanced than feared, and that American momentum, military planning, scientific ambition, and wartime bureaucracy developed a force of their own. The uncertainty does not make the story less serious. It makes it more human. People acted under fear, partial information, and pressure, which is exactly when humanity likes to make its largest decisions. You stand in a meeting room where the air is stale and warm. Ashtrays are full, a map curls at the edges. Someone taps a pencil against a notebook. The language is technical cross-sections, critical mass, neutron economy, enrichment, tamper, yield. Technical language can make terrible choices feel cleaner. It turns fear into diagrams. It turns future destruction into numbers on a page. Yet the people making those marks are not machines. Some are excited by the scientific challenge. Some are frightened. Some push questions aside because the war seems to demand speed. Some will later regret. Some will defend. Many do both, depending on the hour. The secrecy even affects families. At dinner tables in hidden towns, spouses ask what happened at work and receive smiles, shrugs, or jokes. Letters are censored. Addresses are odd. Children play near fences without understanding what the fences protect. A train arrives with materials under guard. A badge swings against a worker's chest. The small tactile details matter: the stiff edge of a pass, the grit of dust in teeth, the sting of a dry air in the nose, the ache of standing through a long shift. History is not only decisions at the top, it is also feet, hands, lungs, meals, and laundry. Uranium itself becomes processed, purified, converted, enriched, and guarded. It passes through chemistry and machinery, through containers and ledgers, through plants whose scale would astonish earlier experimenters. The element has left the quiet mineral world entirely. It now moves by rail, by code, by military order. Its hidden energy is coaxed not by a lone scientist over a plate, but by an entire nation-state in motion. Factories, universities, soldiers, accountants, machinists, cooks, janitors, mathematicians, and drivers all become part of the chain. Not the nuclear chain reaction yet, but the human one. You feel the pace increasing, though the narration stays soft. A telegraph message clicks. A typewriter bell rings. A guard's flashlight sweeps across a fence at night. The smell of desert sage mixes with gasoline. In a dormitory, someone turns over in a narrow bed, too tired to sleep well. In a control room, a dial drifts and a hand corrects it. In a laboratory, a physicist rubs tired eyes and looks again at a calculation that must be right. Because being wrong has become expensive in every possible meaning of the word, and still, beneath the urgency, uranium remains matter, dense, silent, indifferent. It does not know nation. It does not know fear. It does not know that people have built cities around its separation, or that soldiers guard it, or that scientists whisper about it beneath bare bulbs. It simply follows the laws of the nucleus. That may be the most unsettling thing of all. Human history is loud with motives, flags, grief, pride, and urgency. The atom has no motive. It only has structure. Night settles over the secret sites. Oak Ridge hums under electric light. Hanford stretches across a broad, guarded landscape. Los Alamos sits under stars bright as cold glass. You walk past a fence and hear insects ticking in the grass, a generator throbbing in the distance, boots on gravel, a door closing softly. The element that once coloured glass now sits inside guarded processes and classified rooms. War has entered the laboratory, and the laboratory has expanded until it looks like a country within a country. You breathe the dry night air, feel dust on your skin, and sense that humanity has built a machine not only out of metal and uranium, but out of fear, intelligence, secrecy, and speed. You rise into a pale morning sky above the Pacific, where the clouds are soft, the air is thin, and the engines hold a steady metallic drone that seems almost too calm for the task beneath it. The aircraft trembles slightly around you. Aluminum skin, cold to the touch, carries the vibration into every surface. The cabin smells of oil, canvas, heated wiring, sweat, and oxygen equipment. Men speak in clipped voices. Checklists are read. Instruments glow faintly. Far below, ocean and islands pass in blue silence, and the world feels suspended between ordinary procedure and something no one has ever seen in war. It is August 6, 1945. The city below is Hiroshima, built on a delta where rivers thread through neighborhoods, bridges, streetcars, schools, shops, temples, gardens, and military facilities. Morning has begun. People are walking, sweeping, cooking, cycling, opening shutters, preparing for work. You can imagine sandals on wooden floors, the scrape of a breakfast bowl, the smell of rice, coal smoke, river mud, summer dust, and damp laundry. The air is warm already. Cicadas call with their bright, relentless sound, as if nature has no interest in human scheduling. The mainstream fact at the centre of this moment is stark. The United States dropped an atomic bomb called Little Boy on Hiroshima on August 6, 1945. It was a uranium-235 gun-type weapon, and it exploded above the city with a force usually estimated at around 15 kilotons of TNT. A second atomic bomb using plutonium was dropped on Nagasaki on August 9th. Japan announced its surrender on August 15th, and the formal surrender took place on September 2nd, ending the Second World War. You do not need to rush past those dates. Let them sit in the room quietly. History sometimes asks for a softer voice, not because events are small, but because they are too large for shouting. From the aircraft, the target is a shape of streets and water. The bomb bay opens. Cold air moves through metal space. A final sequence unfolds. Technical, practiced, almost unbearably ordinary in its precision. Little boy falls away. For a short time, it is simply an object moving through air, heavy, silent, governed by gravity and design. Inside it, pieces of enriched uranium are arranged so that, at the right moment, a rapid assembly can create a supercritical mass, the chain reaction happens in a fraction of a second. Neutrons multiply, nuclei split, energy releases with a violence that belongs to physics, yet lands fully inside human life. Then there is light. Not light like sunrise, not light like fire. A flash so intense it seems to erase shadows and then create them again in strange, permanent ways. You feel the imagined heat against your face as a dry, impossible wave. The atmosphere cracks into brightness. A pressure wave expands outward, flattening air itself into force. Windows burst. Roof tiles lift. Walls fail. The city's familiar sounds become one vast roar, then splinter into thousands of smaller sounds. Timber breaking, glass raining down, people calling out, dust rushing through streets, fires beginning in scattered places. The smell changes too, from morning cooking and river damp to smoke, burned wood, plaster dust, hot metal, and the sharp mineral scent of destruction. You walk, gently and carefully, through the edge of the ruined city as the narration keeps its distance from what should not be lingered over. The ground is gritty underfoot, ash settles on your sleeves, the air is thick enough to taste. You hear water moving under bridges, strangely calm, while above it the city has been transformed into heat, shadow, and debris. A bicycle lies twisted near a road. A lunchbox sits where a child once carried it. Paper flakes drift in currents of hot air. Human grief is everywhere. But this telling stays with the broad shape, because respect sometimes means not staring too closely. The bomb does not only destroy with blast and heat, it introduces radiation injuries into the experience of war on a citywide scale. Many people who survive the immediate explosion later suffer from radiation sickness, burns, infection, and long-term illness. Doctors and nurses, many injured themselves, try to work in shattered hospitals with little water, few supplies, and confusion about the strange symptoms appearing around them. You smell disinfectant where it can be found, smoke where it cannot, and the sour fear of a city that does not yet have language for everything happening inside bodies. This is where uranium changes from a scientific and military secret into a public fact written across the sky. The element's hidden power, once buried in ore and measured by instruments, becomes visible to the entire world as a new category of destruction. Newspapers struggle to explain it. Governments craft statements. Scientists react with awe, dread, justification, sorrow, pride, and horror, sometimes all within the same person. The phrase atomic age enters public imagination. People begin to understand that war has acquired a scale that can threaten civilization itself. Humanity has not merely built a stronger explosive, it has crossed into a world where matter can be made to release the energy of the nucleus. A quirky tidbit rests uneasily inside the seriousness. Little boy, the uranium bomb was not tested as a complete device before being used over Hiroshima. The design was considered reliable enough because the gun-type assembly was technically simpler than the plutonium implosion design tested at Trinity. Also, enriched uranium was extremely scarce, so there was not much material to spare for a full test. This means the first full wartime use of that design was also its first complete real-world detonation. It is a detail with a strange, cold confidence to it, the kind that makes you want to check every drawer in history and ask who approved the paperwork. On the ground, confidence means nothing. People search for relatives. Fires spread. Rivers fill with those seeking relief from heat and thirst. The city's geography, once graceful with its branching waterways, becomes a map of survival. Bridges stand or fail. Streets vanish beneath debris. Smoke turns the sky brown-grey. The atmosphere feels both loud and muffled, as if the blast has struck not only buildings but time itself. You place a hand against a surviving stone wall, and it is warm. Dust coats your palm. Somewhere a bell frame stands without its bell. somewhere a clock has stopped at the moment of light. Historians still argue whether the atomic bombings were necessary to end the war quickly, whether Japan was already close to surrender, how decisive the Soviet Union's entry into the war against Japan was, and how much the bombings also served as a signal in the emerging rivalry with the Soviet Union. The debate is not a tidy classroom exercise. It involves military estimates, diplomatic messages, Japanese leadership divisions, American casualty projections, imperial politics, moral philosophy, and the memories of survivors. The arguments continue because the decision sits at the crossing of fear, strategy, racism, revenge, urgency, and the terrible arithmetic of war. You move through the first public reactions. In some Allied cities, people celebrate the war's approaching end. Families who fear losing sons, fathers, brothers, and husbands in an invasion of Japan feel relief. Soldiers hear the news and imagine going home. In other rooms, scientists who helped create the weapons sit with a deepening unease. Some had acted from fear that Nazi Germany might build such a weapon first. Germany has already surrendered by this point, and now the bomb has been used against Japan. The purpose has shifted, or perhaps revealed another layer. Moral certainty becomes harder to hold. In Hiroshima, certainty is not the first concern. Water is, shelter is, names are. The city is full of people trying to understand whether their lives still have a shape. You hear sandals dragging through dust, the crackle of small fires, the hiss of steam where water touches hot surfaces, the low murmur of prayers. The smell of smoke clings to hair and cloth. Summer heat presses down without mercy. Night eventually comes, but not as comfort. Fires glow. The sky pulses red in places. The rivers reflect trembling light. Then, in the wider world, imagination begins to mutate. One bomb, one city, one flash, and suddenly every capital city on Earth must think differently. Military planners think about stockpiles. Politicians think about influence. Scientists think about control. Ordinary people think about basements, sirens, and whether the future has become too bright to look at directly. Uranium is no longer hidden in technical language. It has become a word attached to survival. A strange psychological split appears almost immediately. The same physics that can destroy a city might also power ships, produce electricity, treat disease, and open new fields of research. Humans are very talented at standing beside a terrifying thing and asking whether it can also boil water. Gentle sarcasm aside, the dilemma is real. Nuclear science is not identical with nuclear weapons, but the first great public revelation of atomic energy arrives through devastation. That origin stains everything that follows. Every peaceful promise has to speak beneath the shadow of the mushroom cloud. You picture survivors, later called hibakusha, carrying memory into decades that do not always want to listen. Their testimony becomes essential to the human meaning of the atomic age. They describe light, heat, silence, confusion, loss, and the long aftermath of illness and stigma. Their voices make abstract policy human. Without them, Uranium's story might become only a tale of machines, generals, presidents, and equations. With them, it remains also a story of lunchboxes, school uniform, riverbanks, family names, and mornings interrupted. The day fades in your mind, though the consequences do not. Ash settles, smoke thins. The rivers keep moving toward the sea with a patience that feels almost impossible. Above the city, the sky clears by degrees, indifferent and blue. Somewhere far away, officials prepare announcements. Somewhere else, people cheer the war's nearing end. In Hiroshima, people gather what can be gathered and call out for those who do not answer. You stand at the edge of the chain city and feel the warm dust under your feet. Uranium has made itself visible not as a glow in glass, not as a mark on a photographic plate, not as a calculation on a blackboard, but as a rupture in human history. The element has become a question that will not leave the century alone. How much power can a species hold without being remade by it? How much fear can be called security? How much suffering can be placed inside the word necessity? The night air cools at last. Smoke hangs low. A few small sounds return water, insects, footsteps, the soft movement of cloth. The atomic age has begun, not with triumph alone, and not with grief alone, but with a terrible mixture of relief, shock, argument, and silence. You breathe slowly, tasting dust and summer heat, and you understand that from this moment, humanity will live under a new kind of sky. You step into the post-war world, where the air smells of fresh paint, cigarette smoke, new plastic, and nervous optimism. Cities rebuild. Families buy radios and refrigerators. Governments speak in polished phrases about peace, progress, and security, while military planners quietly draw circles on maps. The atomic age has not ended with one terrible revelation. It has spread into speeches, classrooms, factories, submarines, deserts, and power stations. Uranium is no longer only a wartime secret. It is becoming a promise, a threat, and a very complicated household word. You hear the hum first, not an explosion, not a siren, but a deep industrial hum behind concrete walls. It is the sound of turbines, pumps, generators, ventilation systems, and lights that never seem to sleep. In the years after the Second World War, leaders and scientists begin to ask whether the heat from controlled nuclear fission can be used like any other heat source to boil water, make steam, spin turbines, and produce electricity. In one sense, the idea is almost ordinary. A nuclear power plant still makes steam. The very fancy atom, after all that drama, is mainly hired to do kettle duty. History has a strange sense of humour. You walk through an early nuclear facility in your imagination. The floor is smooth beneath your shoes. The walls are thick. The air is cool and filtered, carrying faint smells of metal, disinfectant, warm oil, and concrete dust. Signs are painted in careful lettering. Pipes run overhead in disciplined lines. Behind shielding, uranium fuel sits inside a reactor core, where fission releases heat at a controlled rate. Control rods absorb neutrons. Coolant carries heat away. Operators watch gauges and panels, listening to fans and pumps with the alert calm of people responsible for invisible fire. The mainstream historical fact here is clear after the war. Uranium became central to civilian nuclear power as well as military strategy. The United States launched the Atoms for Peace initiative in 1953, promoting peaceful nuclear technology. While early nuclear power stations such as Calder Hall in Britain and Shippingport in the United States helped demonstrate that reactors could feed electricity into public grids. The same basic nuclear process that had frightened the world was now being placed inside buildings with visitors' galleries, press releases, and the word future written all over it in very confident ink. Electricity gives uranium a new public costume. Posters show glowing cities, clean kitchens, bright classrooms, and smiling children doing homework under lamps powered by tomorrow. Nuclear energy is presented as modern, efficient, almost magical. Coal is dirty, smoky, and old-fashioned. Oil belongs to geopolitics and price shocks. Uranium, by contrast, seems compact and brilliant. A small amount of fuel can release an enormous amount of energy. That fact is real, and it gives nuclear power its genuine attraction. But the public language often becomes softer than the engineering. Brochures do not usually smell like hot coolant pumps or mention waste storage in the same cheerful font as progress. You stand near a viewing window. Beyond it, machinery glows under white lights. A technician's badge brushes against a lab coat. A pencil taps a clipboard. The atmosphere is almost ceremonial. Everything is labelled, monitored, shielded, and double-checked. Yet the calm depends on systems working correctly. Nuclear power asks for trust in design, training, regulation, maintenance, and institutions. It is not only physics, it is bureaucracy with neutrons. Then you travel down to the sea, where uranium's post-war life becomes quieter and more secretive. A nuclear-powered submarine slides through dark water, its hull cold against the pressure of the deep. Inside, the air smells of metal, warm machinery, human bodies, coffee, cleaning fluid, and recycled breath. There is no sunlight, there is no fresh breeze, there is only the steady pulse of systems and the soft creak of a vessel surrounded by ocean. Nuclear propulsion changes naval power because a reactor can run for long periods without oxygen and without frequent refueling. Submarines can stay submerged for extraordinary lengths of time, hidden beneath waves while politics rumbles above. A quirky tidbit surfaces here like a periscope. In January 1955, the USS Nautilus, the first nuclear-powered submarine, sent the message underway on nuclear power. It was a short phrase, almost modest, yet it marked a transformation in naval history. Later, Nautilus travelled beneath the North Pole, turning a region of ice and myth into a route for nuclear machinery. Imagine sailors moving under polar ice in a steel vessel powered by uranium, while above them there is only frozen silence, wind, and moonlit snow. It sounds like science fiction wearing a navy uniform. The Cold War gives uranium a double life. In power stations, it is the fuel of peaceful modernity. In enrichment plants and weapons facilities, it is part of an arms race that fills the second half of the 20th century with anxiety. Uranium-235 can fuel certain reactors and weapons. Uranium-238 can absorb neutrons and eventually lead to plutonium production in reactors. Nuclear strategy becomes grim architecture of deterrence, stockpiles, delivery systems, early warning radar, bomber routes, missile silos, and submarine patrols. Politicians talk about balance. Generals talk about capability. Ordinary families hear sirens tested in towns and wonder whether the basement is any kind of shelter at all. You step into a 1950s classroom during a civil defense lesson. The floor smells of wax. Chalk dust floats in the sunlight. A projector clicks and whirs. Children sit at small desks, touching the cool metal legs of their chairs, listening to instructions about what to do if a flash comes. Some are frightened. Some are bored. Some probably whisper jokes, because children are humanity's finest defense against solemn absurdity. The atmosphere is strange pastel school walls, lunchboxes, maps, and the shadow of nuclear war folded into routine. The age teaches people to imagine the unthinkable as a drill. Above ground, test explosions become spectacles and warnings. In the deserts of Nevada, in the Pacific, in Soviet test sites, in British, French, and Chinese programs, nuclear weapons are tested in air, underground, underwater, and across remote landscapes often described by officials as empty. But empty is one of those words governments use when they would prefer not to notice who lives nearby. The sound of a test can arrive as a distant thunder. The flash can turn night into a brief artificial dawn. The smell afterward may include dust, ozone, hot rock, and fear. Fallout becomes a word people learn with their breakfast news. Historians still argue whether nuclear deterrence truly prevented a direct great power war, or whether humanity survived the Cold War partly through luck, restraint, and several frightening near misses. Some scholars see nuclear weapons as a grim stabilizer, making leaders cautious because the cost of war became unimaginable. Others emphasize accidents, misread signals, political crises, and human fallibility. The argument remains unsettled because the evidence is tangled with events that did not happen. How do you prove a catastrophe was prevented? How do you measure the weight of a war that fear kept sleeping? Uranium sits at the center of that uncertainty. Quiet inside warheads, fuel rods, stockpiles, and storage cylinders. Its presence changes diplomacy. Treaties begin to limit tests, monitor materials, and slow the spread of the weapons. Inspectors count, seal, measure, and verify. Nations argue over enrichment levels, reactor types, fuel cycles, and sovereignty. A number becomes politically charged. Low enriched uranium may be used for power reactors. Highly enriched uranium can be weapons usable. The difference is technical, but the consequences are global. A percentage on paper can make diplomats lose sleep, which is quite an achievement for arithmetic. At the same time, nuclear medicine expands. Reactors produce isotopes used in diagnosis and treatment. Research reactors serve universities, hospitals, and industry. Nuclear science becomes not only a military subject, but part of medicine, agriculture, materials testing, and basic research. This quieter work rarely appears in the public imagination with the same intensity as mushroom clouds or cooling towers, but it matters deeply. Uranium enables reactor systems that produce useful isotopes, helping doctors see inside the body, treat certain cancers, and sterilize medical equipment. The element remains morally mixed, not because the atom has morals, but because people do. You return to the power plant at dusk, outside. The cooling towers rise pale against a purple sky, giving off plumes of vapour that look dramatic but are often just water mist, nature's least villainous special effect. Crickets begin in the grass. The air smells of damp earth, cut weeds, river water, and faint industrial warmth. Workers leave through security gates, lunch boxes in hand. Inside, the reactor continues its controlled heat. Lights burn in homes miles away. A kettle boils. A radio plays softly. Someone reads in bed under electricity that may have passed through the hands of uranium. Turbines, wires, and trust. But peace is never simple in this story. Nuclear power brings questions about accidents, waste, cost, and public consent. Weapons bring questions about survival, deterrence, and morality. The Cold War turns uranium into both shield and sword, both lamp and shadow. It powers submarines that hide in oceans. It helps generate electricity for civilian grids. It sits in treaties, fears, laboratories, and campaign speeches. It becomes part of the background noise of the modern world, sometimes noticed, often ignored, always present. Night deepens, the power station hums. Far away, a submarine moves beneath black water. Farther still, a missile silo rests under cold prairie stars. In a hospital corridor, a machine clicks softly as a patient waits. In a child's bedroom, a lamp glows beside a book. Uranium has entered all these rooms without becoming simple in any of them. You feel the cool evening air on your hands, hear the low mechanical rhythm beyond the fence, and understand that the post-war world has learned to live beside an element that can warm a city, propel a vessel through darkness, or hold civilization in a very uneasy peace. You step onto a dry plateau where the wind moves low over sagebrush, sand, and broken stone. The sky is wide enough to make every human plan feel small, which is rude of the sky, but not inaccurate. Under your boots, the ground is pale, gritty, and warm from the sun. A fence line hums faintly in the breeze. Somewhere in the distance, a truck engine growls, then fades. The air smells of dust, diesel, hot metal, and the bitter green scent of desert plants crushed under tires. Here uranium is not a bright promise in a speech or a quiet fuel rod behind thick walls. Here it is work. It is ore hauled from the earth. It is men and women driving roads before sunrise, lamps bobbing in tunnels, drills biting stone, dust settling into hair, clothes, lunch pails, and lungs. It is wages, danger, pride, need, secrecy, and sometimes neglect wrapped together so tightly that no one can pull out one thread without disturbing all the others. You walk toward the entrance of a mine. The opening is dark and cool, breathing air from underground. As you enter, The heat of the day falls away. Your fingertips brush rough timber supports. The wall is damp in places, powdery in others. Water ticks from stone into shallow puddles. The sound of a drill starts deeper inside, harsh and pulsing. A mechanical insect trapped in the mountain. Dust hangs in the beam of lamp. It tastes mineral and dry on your tongue. A mainstream fact settles heavily here during the 20th century. Uranium mining expanded rapidly to supply nuclear weapons programs and later civilian reactors, and many miners, including indigenous workers in regions such as the American Southwest, were exposed to dangerous levels of radon gas, radioactive dust, and poor ventilation. Long before safety rules became stricter, workers often laboured without full knowledge of the risks. Some families later faced illness, loss, and long legal struggles for recognition and compensation. The mine is not only an industrial place, it is also a social place. You hear boots scrape, a lunch tin open, a joke spoken too loudly over machinery, a cough swallowed because there is work to finish. You smell tobacco, sweat, damp canvas, lamp fuel, and powdered rock. A miner's hand, rough with calluses, closes around a tool handle polished by repetition. Someone thinks about a paycheck. Someone thinks about children at home. Someone thinks about a truck payment, a roof repair, a winter coat. History likes to talk about materials, but materials are carried by bodies. In the Navajo Nation and other indigenous communities, uranium extraction left deep scars. Mines and mills brought employment, but also contamination of land, water, and homes. Some abandoned mine openings remained unsecured for decades. Waste rock was sometimes left near communities or used in construction without proper understanding of danger. Dust blew across grazing land. Water sources became suspect. Sheep moved through landscapes where invisible hazards had joined old trails. The tragedy is not only exposure, it is the insult of being told that progress is national, while the burden is local. You step outside again, and the light feels too bright. A dry wind touches your face like warm paper. Near a mill site, ore is crushed and chemically processed to extract uranium concentrate, often called yellow cake. The name sounds almost friendly, like something served with tea by a dangerously literal baker. In reality, it is a powdery uranium oxide concentrate, usually yellow to dark olive or brown depending on processing. It travels in drums, enters fuel cycles, weapons programs, and contracts. A cheerful name does not make a hazardous material less serious, but it does make history sound briefly ridiculous, which is not always helpful. The mill has its own atmosphere. Conveyor belts rattle, crushers grind, tanks and pipes hold acidic or alkaline solutions. The smell is sharp, chemical, and dusty. Fine particles settle on railings and boots. Workers move through noise and vibration, checking gauges, valves, and filters. Behind the product lies a much larger volume of leftovers tailings. These are the crushed, processed remains of ore, still containing radioactive decay products, heavy metals, and chemical residues. Tailings piles and ponds become long-term environmental problems because uranium's companions do not politely disappear once the useful fraction is removed. A quirky and rather unsettling tidbit belongs to a different landscape. In parts of the American West during the uranium boom, prospectors used Geiger counters almost like treasure hunting instruments, wandering hillsides, old claims, and desert washes while listening for clicks. Magazines and advertisements encouraged the dream of striking it rich. There were even uranium rush stories, complete with hopeful amateurs, battered vehicles, and the idea that the next lucky outcrop might change a life. Imagine a prospector in dusty boots holding a detector over stone, waiting for the clicks to rise, as if the earth were whispering lottery numbers. But the romance of the prospector hides a harder truth. Radioactivity is not just a signal of value, it is also a warning. Radon, a radioactive gas produced in uranium decay chains, can accumulate in underground mines. Its decay products can lodge in the respiratory system when inhaled with dust. Scientific knowledge of mine hazards existed in parts of Europe from earlier studies, but that knowledge did not always translate into timely protection for workers elsewhere. Ventilation, monitoring, masks, and regulations came unevenly, often after harm had already spread through families and communities. Scholars continue to debate how responsibility should be divided among governments, mining companies, military agencies, scientific advisors, and regulators. Some emphasize the pressures of Cold War urgency and the imperfect knowledge available to individual workers. Others point to evidence that hazards were known well enough to demand stronger action sooner. The disagreement is not about whether harm occurred. It is about who knew, when they knew it, what they chose not to say, and how long ordinary people were left to breathe the consequences. You walk beside an abandoned mine, and the silence is not peaceful exactly. It is watchful. Rusted equipment sits under sun. A warning sign creaks on a post. Dry grass scratches against your trousers. The mouth of the mine is blocked, but the hillside still looks wounded, is rock cut open and left to weather. Rainwater, when it comes, can move through disturbed material. Wind can lift dust. Children, livestock, and curious visitors do not always understand invisible danger. A landscape can look empty and still be full of unfinished business. Then there is waste from reactors and weapons production, a quieter problem because it often sits behind fences, inside casks, pools, vaults, or heavily monitored sites. Used nuclear fuel remains intensely radioactive and thermally hot for years, requiring cooling and shielding. Some radioactive waste stays hazardous for time spans that dwarf normal political planning. Governments are good at promising 10-year strategies. Uranium's byproducts prefer to think in centuries and millennia. Very inconsiderate of them. You enter a storage facility in imagination. The air is cool, dry, and filtered. Concrete walls hold a steady chill. Lights buzz overhead. Security doors close with thick final sounds. Metal casks stand in disciplined rows, massive and silent. Their surfaces feel cold to the eye, even if inside they contain the memory of heat. Workers move carefully, following procedures written in exact language. Sensors watch temperature, radiation, pressure, and movement. Here the human sense of time changes. The question is not just how to store something until next year. It is how to communicate danger to people who may not speak your language, share your symbols, or inherit your institutions. That problem becomes almost philosophical. How do you mark a waste site for thousands of years? A skull and crossbones might not mean the same thing forever. A fence will rust, a government may fall, a language may shift. Some proposals have imagined hostile architecture, warning landscapes, durable markers, even cultural memory systems that pass caution down through generations. There is something haunting about designing a message for distant strangers. Do not dig here. Do not drink here. Do not mistake this place for treasure. It is bedtime storytelling from the least cozy committee imaginable. You feel the cool surface of a concrete barrier beneath your palm. It's smooth, slightly dusty, and indifferent. Outside. Evening lowers over the site. A bird calls once from a utility pole. The sky turns lavender. Beyond the fence, ordinary life continues: roads, groceries, school buses, kitchens, dogs barking at nothing important. Nuclear waste asks ordinary communities to live beside extraordinary timelines. Some accept facilities for jobs and investment. Some resist because they distrust institutions that have broken promises before. Both responses are human. A paycheck and a protest sign can come from the same kind of love for home. Uranium also carries uneasy promises. Nuclear energy produces electricity with very low direct carbon emissions during operation, which makes it part of serious discussions about climate change and energy security. Reactors can run day and night, not dependent on sun or wind. That reliability matters, yet mining, milling, enrichment, accidents, waste, cost, and weapons proliferation remain concerns. The element offers power without smoke at the chimney, but not without consequences. Nothing in history is free, especially not the things advertised as clean, limitless, and easy. Those words should always make you check the basement. You stand once more on the desert plateau as night gathers. The ground releases stored heat. Dust cools under your boots. Sagebrush darkens into low shapes. Far away, a light blinks on a tower. The wind carries no clear answer, only the dry whisper of grass and grit against stone. Uranium's cost is not one story. It is many miners in tunnels, families near tailings, engineers designing storage, communities arguing over consent, physicians tracking disease, officials signing forms, and landscapes asked to remember what people would rather forget. The element remains quiet through all of it. It does not apologize, defend, persuade, or promise. Those are human activities. Uranium simply exists with its density, its isotopes, its decay chains, its energy, and its long afterlife in the places people have disturbed. You breathe slowly in the cooling dark and feel the rough earth beneath your feet. The lesson is not that power should never be used. It is that power must be followed all the way down, into tunnels, water tables, lungs, fences, ledges, and the long patience of stone. You stand in a quiet control room where the present feels less like a finish line and more like a dimly lit waiting room. Screens glow softly. Fans breathe behind panels. A chair creaks as someone shifts their weight. The air smells of warmed plastic, coffee, floor cleaner, and the faint metallic dryness that lives in places where machines are trusted to stay awake. Outside the thick windows, evening settles over a nuclear facility, turning fences into dark lines and cooling towers into pale shapes against the sky. Uranium is no longer a mysterious stone, not merely a colorant, not only a wartime material, not just a fuel. It has become a long conversation humanity keeps having with itself. You can hear that conversation in government offices, climate conferences, engineering schools, courtrooms, protest camps, naval bases, hospitals, mining towns, and quiet kitchens, where electricity hums through the wall. The element has become part of policy, memory, fear, hope, and accounting, which is perhaps the least glamorous fate for a cosmic metal. But here we are. Even the atom must eventually meet paperwork. The mainstream fact at the centre of this present age is that uranium remains essential to most nuclear power reactors, where controlled fission produces heat used to generate electricity. In many reactors, uranium fuel is enriched so it contains a higher proportion of uranium-235 than natural uranium. That fuel sits in carefully engineered assemblies, surrounded by coolant, control systems, shielding, sensors, and procedures. The heart of the process is simple to say: atoms split. Heat is released, water becomes steam, turbines turn, electricity flows. The reality is more demanding maintenance schedules, safety culture, regulatory review, emergency planning, waste handling, security, training, metallurgy, chemistry, and human attention. You walk along a corridor in a modern plant. Your footsteps sound soft against polished flooring. The walls are clean and pale. Behind locked doors, instruments measure what your body cannot sense. Radiation has no smell, no taste, no sound. That silence has always been part of uranium's power over the imagination. A flame warns you with light and heat. A storm announces itself with wind. Uranium's deeper activity asks for instruments as models, trust, and caution. It makes the invisible political. Beyond the plant, a town continues its evening. A grocery store sign buzzes. Someone carries a bag of oranges to a car. A dog barks at a bicycle, performing its sacred duty. Lamps turn on in windows one by one. Some of those lamps may be powered by uranium. The people beneath them may support nuclear energy, oppose it, ignore it, or only think about the bill. Modern life often depends on systems people rarely see. Electricity arrives as a switch, not as a fuel cycle. The wall socket is very quiet about its ancestry. In the age of climate anxiety, uranium has gained another role. Nuclear power produces large amounts of electricity with very low direct carbon dioxide emissions during operation, which makes it attractive to some energy planners trying to reduce fossil fuel use. Reactors can run steadily through night, calm weather, and winter clouds. This reliability gives nuclear energy a seriousness that cannot be dismissed with a slogan, yet concerns remain cost. Construction delays, waste, accidents, mining impacts, security, and the link between civilian nuclear technology and weapons knowledge. Uranium offers a cleaner chimney, not a simple conscience. You enter an international conference hall, softly carpeted and brightly lit. Translation headsets rest beside water glasses. Delegates murmur in many languages. Papers slide across tables. The air smells of coffee, perfume, fabric, and diplomatic patience, which is somehow both expensive and exhausted. Here uranium becomes a matter of safeguards and trust. Inspectors verify nuclear materials. Treaties attempt to limit weapons spread. Governments argue over enrichment, reactor rights, sanctions, inspections, fuel supply, and national pride. A centrifuge can be a machine, a symbol, or a crisis, depending on who owns it and who is asking questions. That is one of uranium's strangest modern gifts. It turns technical details into world affairs. Percentages of enrichment, kilograms of material, types of reactors, spent fuel inventories, and inspection access can shift the mood of entire regions. The element remains dense and silent, while human systems around it become loud with suspicion. It is almost funny, in the driest possible way, that something with no opinion can create so many meetings. Uranium does not negotiate. People do nervously. A quirky tidbit brightens this serious room for a moment. Natural uranium is not all the same age in the way a coin is minted on a single date. Its atoms belong to decay chains and cosmic histories stretching back billions of years. Some uranium atoms in rocks today have been slowly transforming since Earth was young, ticking through half-lives so vast that human civilization looks like a candle flicker. Uranium-238 has a half-life of about 4.5 billion years, close to the age of the Earth itself. So when you hold the idea of uranium in your mind, you're holding a clock almost as old as the planet. Very dramatic, for something that may end up in a fuel pellet shaped like a tiny ceramic button. You step into a fuel fabrication facility. The space is controlled, precise, and oddly calm. Uranium powder is processed into ceramic pellets, which are stacked inside metal tubes to form fuel rods. The pellets are small, smooth, and dense. You imagine one resting in a gloved hand, dull and unshowy. It does not look like destiny. It looks like a quiet industrial bead. Yet within a reactor, such pellets can release astonishing energy over years. The touch here is indirect, through gloves, tools, and protocols. The sound is not thunder, but the hiss of ventilation and the soft clatter of equipment. The future of uranium is still unsettled. Some countries are extending the lives of existing reactors. Others are building new ones. Some are investing in small modular reactors, advanced fuel cycles, and designs that promise improved safety or reduced waste. Some nations are closing plants and turning elsewhere. Public opinion shifts after accidents, energy shortages, price spikes, wars, and climate reports. Nuclear power is never only a technical choice. It is also a story a society tells about risk. Which danger feels nearer carbon in the sky? Radioactive waste underground? A reactor accident? Dependence on imported fuels? Or weapons proliferation? The answer changes by country, generation, and lived experience. Researchers still disagree about whether nuclear energy should grow dramatically as part of a climate solution, or remain limited because of cost, waste, and risk. Engineers may emphasize reliability and low operational emissions. Critics may point to unresolved storage problems, construction overruns, and the possibility of catastrophic failure. Energy analysts argue over timelines, grids, financing, and public trust. The argument continues because uranium sits at an uncomfortable crossing point. It can help solve one danger while carrying others forward. History rarely gives humanity clean tools. It prefers complicated ones, possibly because history enjoys watching committees sweat. You travel now to a deep geological repository imagined in stone and shadow. The air is cool. Your hand touches rock that feels dry and ancient. Lights run along a tunnel, casting golden pools into the distance. Containers as it's designed to endure, surrounded by engineered barriers and stable geology. The goal is to isolate dangerous waste from the living world for spans of time that make ordinary politics look like a mayfly with a calendar. There is something humbling in this architecture. It asks people to think like ancestors and descendants at once. The sound here is minimal boots on stone, ventilation moving air, the distant echo of machinery. The smell is mineral, clean, and dry. A repository is not a tomb exactly, though it has that feeling. It is a promise made to people who will never vote, never sign the contract, never attend the meeting. You sense the strange tenderness of that responsibility. The future cannot speak, yet it must be protected from the leftovers of present power. Uranium also remains inside weapons, both dismantled and deployed, both declared and hidden. Warheads age, materials are monitored, treaties weaken or strengthen depending on politics. Nuclear arsenals are justified as deterrence, criticized as existential danger, modernized in the name of stability, and feared because stability is only as strong as the people and machines interpreting the next warning signal. Somewhere, in guarded rooms and silent submarines, uranium and plutonium still sit inside, designs meant never to be used but always to be believed. It is a strange kind of peace, built on the promise of unacceptable fire. And yet uranium's story is not only dread. In hospitals, nuclear science helps diagnose illness and treat disease. In laboratories, radiation and isotopes help researchers trace processes, test materials, sterilize equipment, and understand the natural world. In planetary science, uranium-led dating helps estimate the ages of rocks, giving Earth's history a measurable depth. The same elemental family that frightens can also reveal time, heal bodies, and illuminate hidden structures. That moral mixture is not a contradiction. It is the human condition, wearing a lab coat. You stand outside as night fully arrives. The facility lights glow behind you. Above, the stars look calm, although stars are not calm at all, which is their little trick. The uranium beneath human management came from cosmic violence and geological patience. It entered hands, homes, mines, reactors, treaties, and memories. Its future may include new reactor designs, tighter safeguards, better waste storage, cleanup of old harms, or renewed danger if fear outruns wisdom. No single ending fits it. Uranium does not close like a book. It persists like a question. And now the scene softens. The machines grow quieter in your imagination. The control room lights dim to a gentle blue. Far beyond the fence, the town settles under warm windows and slow traffic. Somewhere a kettle cools on a stove. Somewhere a bedside lamp glows beside an open book. You let the heavy elements sink back into silence. not forgotten, but held with care. The stone, the fuel, the warning, the promise, all become still for a moment. Night spreads across mines, cities, oceans, laboratories, and sleeping fields. The earth turns slowly. The atoms keep their ancient clocks. You breathe in, breathe out, and let history loosen its grip, leaving only darkness, distance, and a soft remaining glow.